We'll see how Kruskal algorithm works. So Kruskal algorithm is similar to Prim's algorithm, but what Kruskal algorithm does is there is no source vertex, nothing. So always Kruskal algorithm picks minimum edge among all the edges of the graph. So that means, so when you start Kruskal algorithm, so in the result first A to B will be selected, otherwise B to D, otherwise A to C. Okay. So let's blindly follow the Kruskal algorithm. Kruskal algorithm's idea is very simple. Pick the minimum edge and go, next time pick the second minimum. In that way keep continuing until you form a tree. Okay, let's see Kruskal algorithm. So pick up the minimum among all. So that's why Kruskal algorithm and Prim's algorithm, so they are using a strategy called greedy strategy. I can say that Prim's and Kruskal algorithms are a kind of greedy algorithms, where Prim's algorithm has a choice. What is that? Always pick up the minimum edge among all the existing visible edges. Kruskal algorithm says nothing, no visibility, nothing. Pick up the minimum edge among all possible edges. That's why in both algorithms are following greedy choice. So let's continue this Kruskal algorithm. So first let's take AB. When you have choice, so it is implementation dependent. You can either pick up AB or AC. So there is no rule that AB should be picked or A to C should be picked, anything. Okay. So first of all AB. After that, what is the next minimum element? Once this is selected, still 1, correct? Let's take it. What is the next minimum element? Still 1. Let's take B to D. What is the next minimum element? So far 3 ones are gone. We have any one? No. Then do we have 2? Yes. What is that? We have A to D. But if I take A to D, though it is minimum, it is forming cycle. If it forms cycle, don't take it, though it is minimum. That's why, so we never consider this one. Then what is the next minimum we have? Next minimum number is 2. So take it. Again it forms cycle, don't pick it up. What are the other possibilities we have? Next minimum value is 3, correct? We have BE, second one CG. Anything we can take. Let me take BE. Okay. After that, what is the next minimum number? So of course it is 3, right? Then after B, next minimum number is again 3. So that is C to G, correct? Then what is the next minimum number? Next minimum number we have is 4, 4, 4, for everywhere 4. So let's take EF. So which will complete the algorithm, right? So this is about Kruskal algorithm and result. In Kruskal algorithm, what can happen is, example, you have A to B1 and G to F1. Then you might pick AB, after that immediately GF, so that you form disconnected graph, otherwise some connected components. So that is a major difference between Prim's algorithm's result and Kruskal algorithm's result, one property. So Prim's algorithm always ensures your result is connected. Kruskal algorithm in that result goes like disconnected, connected, we can't say. But end of the day, so your result will be definitely spanning tree which is connected. But one thing, what is guaranteed is, Kruskal algorithm gives, here AC1, right? Kruskal algorithm guarantees minimum spanning tree. Prim's algorithm also guarantees minimum spanning tree. And one more thing, if you have choices, generally you have choices, right? Example, there is a graph with A to B, B to C edges and edge weights are 1. Then Prim's algorithm can pick A to B first, otherwise B to C. Even Kruskal algorithm can pick A to B or B to C. What I want to say is, Prim's algorithm, given a choice, it can, given a possibility, it can find out any minimum spanning tree. That means it can find out all possible minimum spanning trees. Even Kruskal algorithm can generate all possible spanning trees, but generally while implementing, only one spanning tree we generate by taking the decision properly, otherwise uniquely, or I can say unambiguously. Example, you have AB, AC. There are 1 and 1 values, right? Which one to pick? Something we have to decide. Something we have to decide to print one spanning tree generally when executing, correct? So which one will be picked? Anything, but definitely based on the decision you take, either AB can be picked or AC can be picked. If you implement a algorithm such a way that AB is picked, then you form one kind of graph. If you implement such a way that AC is picked, you might get another graph. Understand? Of course, tree. So that's why what I want to say is, Prim's and Kruskal are able to print all possible minimum spanning trees, but it depends on our choice, like how you implement matters. But generally we implement such a way that only one spanning tree is printed. Whenever there is an ambiguity or tie like this, whenever tie you encounter, we resolve it, correct? So that is what we do, because we are interested in one minimum spanning tree, not all minimum spanning trees. No one want to generally print all minimum spanning trees, because sometimes it is exponential. If your graph is closely, complete graph, like if it is almost complete graph, then it can have n to the power of n minus 2 spanning trees. To generate them, you require, at least one universe of age of the universe, or more than that. That means you require crores of years. That's why nobody does that, right? So everyone try to print only one minimum spanning tree. So Kruskal can do it and Prims can do it. These two are the famous algorithms which can print minimum spanning tree, or which can generate minimum spanning tree. We'll see the time complexity of Prim's algorithm and Kruskal algorithm one by one.